Alright, so this will be a video on my continuation of my set theory playlist, and I'm going to be taking a little bit of a break from just plain set theory ideas and kind of talk about one of the big applications of set theory, and kind of like why it's why it's so hard to make progress in set theory. This is kind of like the start of a mini series in my set theory playlist. But anyways, so basically, today I'm going to be talking about cardinality and Hilbert's paradox. Now, basically, Hilbert was a mathematician of the last century, and basically he was very famous. He did a lot of, he wrote a ton of different papers, and he worked in pure math, and then he worked in applied math a lot. He's a pretty big deal, probably one of the best mathematicians in history. Maybe after Euler and Gauss and Newton, people like that. But anyway, so Hilbert, came up with an interesting paradox called the paradox of the Grand Hotel. And basically, the idea of it is, let's say that we have a giant hotel that has an infinite amount of rooms. And basically, the idea is, and every one of those rooms is taken. Now, here's where it gets interesting, because let's say someone new wants to go to the hotel. The hotel will always be vacant. There will always be at least one room vacant, because there's an infinite amount of people, so you can always just move them over one room. Like, the person in room 1 goes to room 2, person from room 2 goes to room 3, so on and so forth. You can basically, you can keep adding new guests because it has an infinite amount of rooms. That's kind of the interesting paradox of the Grand Hotel. And keeping that in mind, we're going to get into what I'm going to be talking about today, which is cardinality and what countably infinite means, which I touched on in my index set video. Basically, we have small numbers like 2 squared is 4, but then you can also have some ridiculously large numbers like 10 to the 100, which, in case you don't know, that's Google, and like the company, except with a different spelling. But anyways, you can have 10 to the 100, that's Google, and you can have 10 to the Google, which is Googleplex, and the size of those numbers is colossal. It's actually, I think it was Carl Sagan who said that to write Googleplex, you don't even have enough space in the universe to write it, and so that kind of puts it in perspective. And of course, so the numbers kind of get bigger and bigger. The natural numbers get bigger and bigger. Now, how do we know for sure that that's the case? Well, this is a natural number for sure. And then I can let's say I can do Googleplex plus 1. That's greater than a Google, and I can do Googleplex plus 2. That's greater than Google. I can essentially repeat this process indefinitely because every one of them is a natural number. And so this is why when you deal with finite sets and infinite sets, there are different rules that apply. And so imagine we have a set A, that has 1, 2 all the way to the Google. This let's just say lists all the numbers from 1, 2, 3 all the way to Googleplex. Sorry. And so the size of that set, the cardinality, which is typically denoted with absolute value bars, 10 to the Googleplex. The size of that set's a Googleplex, which is just colossal. We don't really have a good basis to really understand what a Googleplex is. But anyways, I shouldn't say understand, but I should say kind of see really how big that is. It's kind of hard to understand. It's kind of hard to visualize that or imagine that. Basically, so that's the size of really the size of that set. It's what cardinality is, and so the size of the natural numbers has a special cardinality, and it's really denoted by this Greek Hebrew letter aleph, also sometimes denoted as with Beth 0. Basically, this is the smallest finite number, the set that has the smallest infinite cardinality. Because you can have, next video I'll be talking about the continuum hypothesis and what that's all about. But basically, the natural numbers have countably infinite amount of elements. Because you have 1, 2, 3, 4, 5. You know exactly, each element, what the next one's going to be, more or less. It's kind of it's more of when you think about this, it's kind of an intuitive understanding. You kind of know where the next element is. 1, 2, I know for a fact the next element's 3, I know for a fact the next element's 4, so on and so forth. And I can do that for any natural number. And because of that, it has the cardinality of, this is a special cardinality aleph naught. And so what's interesting, though, which I'll touch on in the next video, this is kind of spoiler alert, really, that the size of the naturals, size of the naturals is actually the exact same size as that of integers. And you may be thinking I'm high or something, but basically because naturals are just 0, 1, dot 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 dot, and then that's your naturals, and then I should not write like that. That's your naturals, and then the integers are all of that, but also the negatives, let's say negative infinity or whatever, and then all the way to -2, -1. and all this. And I'll show you why. There's a proof that actually these two elements have the exact same amount of numbers in them, which when I first looked at it, I thought that was really weird, and it is really weird. But I'll explain why it's the case, and there's a proof for why that's indeed the case. So anyways, that's kind of a little bit of intro into what set sizes and cardinality. And so I'll be talking more about that in the next video, which I'll really be on the continuum hypothesis. So I hope you guys enjoy, and I'll see you in the next video.